Hello friends, welcome to Susan and John MathTube. In this video, we are going to derive the wave equation and later we will solve it. Okay, the wave equation is the direct application of Newton's law. That is Newton's second law, F is equal to m into A. In 1747, D'Alembert first solved the wave equation and he showed that its solution represents a wave. This line is very important. Now look at this. Usually when you hear the word equation, you might think about trigonometric equation or a quadratic equation. But wave equation is a differential equation. It's a partial differential equation. And that is why he solved and later he talked about the solution. Anyway, later Euler and Daniel Bernoulli modified and made it into the modern form. Okay, so let's start. So consider an elastic string. Okay, we are going to divide the derivation into three parts. First, we will describe. You can look at the string in this position. In your examination, I want you to draw the picture. So it is fixed at x equal to 0, x equal to L, and later it is distorted. It is moved. Okay, so distort the string at some instant and that time will be measured at t equal to 0 and then the string starts to move. Our aim is to derive like what you call the function which depends on both x and t. Can you see x can take any value between 0 and L. So our derivation depends on x and t. Okay, so that's the description part. Now let's go for some assumption. Now look at this. These physical assumptions are made in such a way that our derivation will be very simple. Now some of you might think, including me, when I was a student, I used to think, if you're giving so much of assumption, what's the point in practical situation? Now look at this. Our assumptions are 1. The mass of the string per unit length is a constant. And by the way, you can, if you want, you can write rho is the density per unit length because later in the derivation, we will consider 2 points x and x plus delta x. And the distance between them is delta x and even in distorted position because we assume the distortions are very small, very small, not exaggerated like I made the parabola like thing. Okay, so the distance between them is delta x. Here also it's negligibly delta x. So the mass will be, because we want to apply F equal to ma and the mass will be approximately rho multiplied by delta x. Okay, so the second assumption and the third assumption, you can download the notes so that you can later make notes of yourself. I'll keep it in the WhatsApp group. You can scan this and you'll find the notes there. Okay, anyway, the physical assumptions are really good and it will work in an ideal guitar string, in a lightweight lab string, but it is not going to work in practical scenarios like the power cables, the cable car, where these equations are widely used to create safety, etc. etc. Anyway, so there are three assumptions. Now, the last part is the derivation. So, how do we deal with this? First, the description. And in description, we talk about fixed one, distortion, and what we need. And in the second part, we talk about the three assumption, which you can make a note later. Now, look at this. Just like I told you, we consider 2 points x and x plus delta x. And since the string is perfectly elastic, see, we are using our assumption. It does not offer resistance to bending. Hence, the tension at P and Q act tangentially. We need this, we need this. Now, we are going for the math part. And before we start, I hope you remember, in any curve, if you have a tangent to the curve at any point, and if the inclination is theta, then tan theta will be the gradient or the slope. It is denoted by m, and later in your high school you learned that this is nothing but approximately the derivative. So don't forget, tan theta is m and tan theta is the derivative, because this is one very important part in the mathematical derivation. Anyway, I hope the picture looks sensible, but it is an exaggerated picture. By the way, do you know, I can never make a picture like this. It is kind of like the wave is moving and I took a snapshot. The wave is moving like this, the string is moving like this, and I took a snapshot. Not the wave, but the string. Okay, so this is an exaggerated version. Since we are freezing time, that means we are making one variable constant, we are going to deal with partial derivative, not the original derivative. There are two variables x and t. You already know two variables x and t. But since we are freezing time in this picture, we are talking about the change in x by treating t as a constant. That's a partial derivative. Okay, now let T1 be the tension at P, T2 be the tension at Q. And if you are not able to see the inclination, I'll draw a line parallel to the axis. It's beta. No need to draw for picture. And this is our alpha. And you know basic physics. And from physics, we can resolve the vectors. And you're going to get vertical components minus T1 sine alpha, T2 sine beta, horizontal. Okay, you know these things. Okay, now comes the advantage of our assumption. Since the string moves only vertically, there is no motion in the horizontal direction. That means the horizontal components will be equal and we can assume it's a constant. And I'm going to call the constant T. Note it down, we need this. Okay, so the total vertical force will be T2 sine beta minus T1 sine alpha. Now if you're confused, let me tell you one thing. Only unbalanced forces cause motion. Look at this. Here they are telling very clearly the horizontal components of the tension must be equal everywhere because of our assumption. And that is why we care only about the vertical force, and the resultant is T2 sine beta minus T1 sine alpha. So we need this, we need this. Now what we are going to do is we are going to calculate the same force using Newton's law. Now applying Newton's second law, in exam you have to write this, it's very, very important. Vertical force will be mass into acceleration. Since rho is the density and delta x is the length, and because of our assumption, we can assume the mass to be approximately rho delta x. And obviously, the acceleration is the second order derivative. Can you see? The acceleration is the second order derivative with respect to time. Okay, now comes the derivation part. According to our picture, the vertical force is T2 sine beta minus T1 sine alpha. And according to Newton, we got this to be rho delta x del square u by del t square, or the second order partial derivative. Now for my advantage, actually I'm going to create tan. I'm going to manipulate everything. I'm going to divide throughout by t. I hope you don't mind if you divide an equation throughout by a non-zero constant. If a minus b equal to c, I can divide this throughout by d. So similarly, I'm dividing throughout by t, and we know that this t is actually t1 cos alpha as well as t2 cos beta. So I'm going to delete this t and I'm going to put t1. Oh no use. So I'll put t2 cos beta. I can put t1 cos alpha. I'm intentionally doing it so that I get an advantage. This will get cancelled and I get tan beta minus tan alpha equal to rho divided by t delta x, and I'll use the notation utt. Easy to write. Okay, now comes pure math. What is tan beta? Come on, I told you tan is the derivative. It's approximately the derivative, and here it will be partial derivative because we are freezing time. Do you remember? What is this alpha, beta, etc.? We froze time, so time is a constant. So basically, this tan beta will become ux at x plus delta x, comma t, because time is frozen, minus ux at x comma t is equal to rho by t delta x u tt. I hope you understood, because Tan is the derivative, but in this case it's a partial derivative because we are ignoring time, or we are keeping time as a constant. And this is the gradient or the derivative at x plus delta x, and this is the derivative at x. Okay, now I'm going to divide throughout by delta x. So I'll get u x plus delta x comma t minus u x comma t, the whole divided by delta x is equal to rho by t into u dt. And next step, I'm intentionally going to take limit delta x tends to 0 on both sides. Now look at this. We have the formula which you learned in first principles. What is f of x plus delta x minus f of x the whole divided by delta x when delta x tends to 0? You learned it in complex, you learned it in first principle. But here, remember there is another character called t. So this is nothing but the second order derivative. Derivatives may like what you call dou by dou x, or the derivative of ux. And on this side, limit delta x tends to 0 cannot tamper anything. So we get rho by t u dt. And we get u xx is equal to rho by t into u tt. And we manipulate it a little bit so that we get the standard form u tt equal to t by rho u xx, and they call it c square. And there's so much explanation, you can read about it. So this is the standard wave equation. Okay, so once more, if you want the notes, you can just scan this and you'll get the notes there. In the next video, we'll derive it. So till then, my friends, bye.